Mm. Okay, thank you, Ntatemba Nambane. Learners, good afternoon, as well as educators. Some of the educators I know they're supporting this program. You're welcome, sir, for madam. Okay, thank you very much, Ntatemba Nambane. Without wasting time, like Ntatemba Nambane indicated, tomorrow we're going to write paper 2, which is the mock. We are preparing you guys for the real actual one for the upcoming exam. Okay. Now, rates and equilibrium graphs. So today I will be concentrating on the rates and equilibrium graphs. Like if you look at the first bullet there, dynamic equilibrium now can be represented graphically. We are going to focus only the factors that are affecting chemical equilibrium. So we know those factors affecting equilibrium, concentration, temperature, and pressure. Now, in this section, we'll also incorporate the rate of reaction and chemical equilibrium. So now the first bullet, if we look at the concentration versus time graph, how to identify which factor between temperature, concentration, and pressure has been affected. So the first part there, if a spike or a drop on only one curve, then concentration was increased or it was decreased. Now, the third bullet, if the spike or a drop on all curves, then the pressure was increased or decreased. If there is no spike or drop in all curves, then you need to know that the temperature was increased or decreased. So let us have a look at this graph below. So now we look at the concentration versus time graph. So now if we don't have a spike, it must be the temperature at T1 there. So because there is no spike, it must be the temperature. So if we have all of them, they must have the spikes. It's either you're going to increase or decrease. It must be the effect of the pressure. Then if we have one spike, it's either the concentration of one of the reactants was added, or maybe the concentration of one of the reactants was removed. So these three bullets, they are so important when coming to the graphs. One spike, only one spike, only one, it must be the concentration was increased or decreased. So let us look at this graph. We want to identify the concentration. If the spike is facing up, the spike is facing up there, so we know the concentration was increased. Then now the second one, if the spike or the drop on all curves, then the pressure. So it must be all curves. Then the pressure is either was increased or decreased. So the spike is facing down, so the pressure was decreased. If there's no spike or drop in all curves, so we know the temperature was increased or decreased. So we are going to look at our delta H there. For argument's sake, if I put delta H to be less than 0, so now if I want to see whether the temperature was increased or decreased, we know the forward reaction and the reverse reaction. So the top one, you look at this side, the forward reaction will be the exo, the reverse will be the endo. So the increase in temperature, if we increase the temperature, we favor the endo. If we decrease the temperature, so we favor the exo. So for 81 there, 81, if I'm going to increase the temperature, meaning I'm going to favor the reverse reaction. So this one will be the favored, which is the endothermic reaction. So meaning the reverse, this side, N2 and H2, it must be the increase. So in your graph, if you see this part, the curve like this, it will be the increase, and the curve like maybe the curve like this one, it will be the decrease. If we have the shape, let me redraw it. If you have the curve like this, it must be the decrease. So now there's a decrease for N2, there's also decrease for H2. But now remember what I've said, the temperature was increased, then to favor the reverse reaction. So N2 and H2 was not favored. So meaning now that cannot be increased in temperature. But if you decrease the temperature, we favor the forward reaction, which is the forward reaction is an exo because the temperature was decreased. Then you look at the ammonia. So decreasing the temperature, we favor the forward reaction. We favor the forward reaction. So we can see that this is an increase in ammonia, which is N3 on the graph there. So meaning the temperature was decreased. So we're going to discuss this part today, okay? So meaning on this graph, specific on this graph, the temperature was decreased. So if you put delta H being less than 0 there, thank you very much. So now moving to the second page, the graph of concentration and rate. So now what is given there is the graph of concentration versus time graph. The reaction below will be used to explain the change to a graph of concentration and rate when changes are made to the equilibrium. So the system is at equilibrium. Then the delta H is less than 0. This is an exothermic reaction. So we have the graph of the concentration versus time. I'm having the graph of the concentration versus time. So this side, I'm going to draw the graph of the rate versus time graph. So I'll be drawing the graph of rate versus time. So now at T0 to T1, the system is not at equilibrium. The two reactants are decreasing, so the product will be formed. But between T1 and T2, the system is at equilibrium. Now, okay. So what can I do now? I want to draw the rate, the graph of rate, then now versus time, the graph of rate versus time in seconds. So I want to draw the graph of rate versus time in seconds. So this will be the rate of the forward reaction. It decreases. This one will be the rate of the reverse reaction. The dotted line, I'm going to use it as the rate of the reverse. The rate of the reverse. The dotted line will be the rate of the reverse. So at T1, somewhere there, so meaning this will be at T1. Between T1 and the T2, the system is at what? The system is at equilibrium. So between T1 and the T2, the system is at equilibrium. So then there is an effect of what? There's an effect of the increase in temperature. So now always when we talk about the increase in temperature, we look at our delta H. So now the increase in temperature, so delta H, which is the forward direction, will be an exo. So now this is the forward, the reverse. Our delta H is less than 0. So the temperature was increased. If you increase the temperature, meaning now we favor the reverse reaction. So the reverse reaction will be the increase in H2 and also N2 there. There is an increase, meaning now I've used the solid line here as the forward direction. I've used the broken line as the reverse. So it doesn't matter. We can also use it, the forward direction, as a dotted line, like in our graph. I can change it. Like in our graph here. They were using, sorry, they were using we can say the forward direction is the dotted line. For the reverse reaction, I can use the solid line. All right. So I'm having that graph there. Okay. Because H2 and N2 is a broken line. So now this will be the broken line. It will represent the reverse. The solid line, it will be the reverse. The broken line will be the forward reaction. All right. So I want to increase the temperature. So increasing the temperature, we favor endo, which is the reverse reaction. So the reverse reaction will be a solid line. The reverse reaction will increasing. Now, in reaction rate, once you increase the temperature, we increase both forward and the reverse. So now we increase both forward and the reverse. But now the one which is favored is increasing more than. So we favor now the reverse reaction is increasing more than, because of the Chatelain principle, is the disturbance on the system. So we want to do what? We want to reinstate the new equilibrium by doing what? By opposing the disturbance. If the temperature is increasing, I need to oppose it. When I need to do what? To work on the system. The system will work on the disturbance by decreasing it. So let me do this. This one, I want the broken one. The broken one, which is the forward reaction, is increasing. Also increasing. But now you look at this side here. All right. This will be the graph of what? This will be a graph of reaction rate versus time. So you highlight this part. You highlight this part. The one which is favored will be on top of the one which is not favored. We favor the reverse reaction. The reverse reaction will be a solid line, because now the increase in temperature, the forward reaction is an exo. So the reverse reaction will be endo. So meaning the increase in temperature, we favor the endo, so which is the reverse reaction. So this is how we draw the graph of rate versus time. Okay. Then the second one, and we need to be careful with this this statement here. So this statement, let me just zoom it to that side. On reaction rate, whichever reaction is favored will always be on top. The one that will be favored will be always on top. So now in this one, we favor the reverse because the temperature was increased. The one which will be favored will be on top. Okay. Now going to the next one. There is a decrease in temperature. So this one, there is a decrease in temperature. So we want to now draw the graph of what? We want to draw the graph of the rate versus time. So I'm going to draw the graph of rate versus time. So it will be rate, the reaction rate versus time here. So now the forward reaction will be this one. The reverse reaction will be the solid line. So now until the equilibrium at T1, the system was at equilibrium between T1 and T2. So we still have the forward and the reverse. Our delta H is less than 0. It's less than 0. Now this time, we're decreasing the temperature. The forward reaction will be an exo. The reverse reaction will be an endo. So the temperature, the T, you decrease the temperature, you favor an exo, which is the forward reaction. So now the forward and the reverse reaction decreases. So now the forward and the reverse reaction decreases. But now, which one is favored? The one that is favored is going to decrease less. We need to be careful with this one. So once we increase the temperature, Coming back to this one, I want to explain something there. So the temperature increased. So now, if you talk about the increase, we talk about more. The one that will be favored will increase more. The one that is favored is going to increase more. Coming to the one, if you decrease the temperature, decrease is less, increase is more. So meaning, if you talk about the decrease in temperature, you are referring to less. So if we decrease the temperature, both forward and the reverse reaction will be decreased. So, but now which one is favored? The forward reaction is favored. This one is forward. This one is reverse. So now we decrease the temperature, we favor exo, which is the forward. So the forward direction is favored, is going to decrease less. So the one which is not favored will decrease more. Now, because this is the disturbance on the system, according to the Chatelain principle, I need to do what? To oppose the disturbance. By doing what? By increasing it, because we need to reinstate the new equilibrium. So this is the graph. This is the graph of the temperature there. So now the one which is favored will be on top of the one which is not favored, which is the reverse. The reverse reaction is not favored. So now to get the broken line to be on top of the solid line, it must decrease less. So decreasing temperature, so now we favor we decrease the temperature, we are going to favor the forward reaction, because forward reaction is an exothermic reaction. Okay, I hope we're still together there. We're still together there. Okay, now what is the effect? The pressure. So the pressure, increasing pressure. So now we want to draw the rate. This one is the, we want to draw the rate, the pressure. Now we look at the gases, the pressure. So this is a gas, and also a gas. All right. So the increase in pressure, I did not explain the concentration graphs. I'm sorry about that. I assumed the concentration is not difficult. I'm sorry about that. Can we just go back to the concentration? The concentration versus time. I'm increasing the temperature. I'm going to favor the reverse. So let us look at the reverse. The reverse, I'm going to favor the reverse, which is the solid line. Let me see there. Increasing temperature. Where I am now, there's an increase. H2 increase in temperature. I'm referring this to H2. The H2, there is an increase. H2 there, if I can use the highlighter. So there's an increase for H2. There is an increase for H2, the concentration versus time graph. So because I'm favoring the reverse, what will be the ammonia? It must be the decrease. Ammonia is going to decrease, so this one is going to decrease. I'm sorry not to mention the concentration versus time graph. So this one, the concentration versus time graph, I'm increasing the temperature. I'm decreasing the temperature. I'm going to favor the forward reaction, which is the ammonia. So the ammonia will be favored. So look at the ammonia on the graph, is an increase. So what about the reverse reaction? So we're expecting to see the decrease for the reverse reaction. So it will be the decrease for nitrogen, that will be the decrease for the hydrogen. I'm sorry not to indicate the decrease and increase on concentration versus time graph. So I was only concentrating to the rate. I'm sorry about that. Okay. Going forward, now there is an increase in pressure. So there is an increase in pressure. If we are increasing pressure, so we are going to look at the volume or the number of moles. So I'm having three volume of a gas for hydrogen plus 1 volume of a gas for nitrogen, the forward, the reverse. I'm having 2 volume this side. So on the left hand side, I'm having 4 volume of a gas. This side, I'm having 2 volume of a gas. So the pressure is in proportion to the volume. So there is an increase in pressure. So the graph is facing up. So the spike is up because there is an increase. If there is a decrease, you'll see the spike will be facing down. Okay, so increase in pressure. If I'm increasing pressure, I'm going to favor the side where I'm having a fewer number of moles of ammonia, or the less number of moles of a gas. So I'm having now increase, I'm going to favor this side. So now this is 2 volume of ammonia. So ammonia will be favored. So now there's an increase in ammonia. So the ammonia is favored because it's a pressure. Okay, we have 3 spikes for pressure. Remember the spikes for pressure: concentration, 1 spike. Concentration, one. There's no spike for temperature, no spike for temperature. But once we have concentration, concentration, 1 spike, pressure, 3 spikes. So there's a first one, there's an increase, there is also a spike somewhere there. So there is also another spike, there is another spike, and also this one. I'm having 3 spikes. But which side is favored? So I'm going to favor the ammonia. You'll see the ammonia is favored. What about the hydrogen? There's a decrease. There's also decrease because now hydrogen and nitrogen, the system favor the forward reaction. Okay, so I want to draw the rate versus time graph. I want to draw the rate versus time graph. So now this is the forward reaction. So this one will be the reverse reaction. So the system somewhere there, the system will be at equilibrium. So I must have T1, and this will be the T2. So there's an increase for both forward and the reverse. So now there will be the increase for both forward and the reverse. The other one is broken line. So must be the increase, both forward and also the reverse. Okay, but I need to know which one will be favored. The one that will be favored is increasing more than. So I'm having now solid and also the broken one. This one is the forward reaction. This one is the reverse reaction. So I'm going to favor the forward reaction. I'm going to favor the forward reaction because I'm having fewer number of moles of a gas. I'm having two volume. So I'm having two volumes. So I'm going to favor the side where I'm having fewer number of moles of a gas. I'm having two volumes. So forward direction will be favored. So this will increase in more than. So this one will increase less. Then ultimately, because there's a disturbance, I need to work on the disturbance. So the graph will be similar to this one. Okay, so we need to be careful with this one. More or less is similar to the temperature. We need to check the temperature. If I can change it, let's see if the temperature increase in temperature. So we want to see whether it's a pressure or in temperature. If I'm increasing temperature, I'm going to favor what? Remember, the forward, the reverse. Delta H is less than 0. So I want to increase the temperature. I'm going to favor an endo. So the endo, which is the reverse reaction. So we need to be careful with this one. I'm talking about the temperature. Because pressure and the temperature, more or less, the graphs are similar for pressure and temperature. So for now, for argument's sake, I want to say, okay, why not temperature but pressure? There's an increase, there's an increase in pressure. Then now what about if it was increasing temperature? I want to see the graph. Okay, I'm increasing the temperature. I'm going to favor the endo, which is what? The reverse reaction. Is it the reverse reaction on top of is it the solid line on top of the broken line? No. You see now, this is how you check the graphs. It can't be the decrease because once the spike is facing up, it must be the increase. So now it can't be temperature, it must be pressure. So because one may say, but now, Mr. Sekharume, the temperature and pressure, the way you draw the graph more or less are the same. No, look at this graph. I'm increasing the temperature. I'm going to favor the reverse reaction. Is it reverse reaction favored there? No. Which one is favored? Is the forward reaction. I hope it's clear to everyone that side. Name. Okay. Okay. So the pressure, remember the concentration is equal to number of moles over the volume. So the volume there was decreased, meaning the concentration was increased. Concentration directly proportional to the number of moles. So now the concentration will be the increase. Then once you see the spike facing up, there is an increase also. Okay. Moving forward, the pressure, we decrease the pressure. So we decrease the pressure. Let us look at the concentration versus time graph. The 3 spikes for 1, 2, 3. 3 spikes are there. But now, ultimately, which side will be favored? The pressure there, the pressure and the volume. So if I'm going to decrease the pressure, I'll favor the side where I'm having the greater number of moles, or it can be greater number of volumes of a gas. So I'm having 4 volume this side, I'm having 2 volume this side. So I want to decrease the pressure. So now is the disturbance on the system. I need to do what? To reinstate the disturbance by opposing the disturbance. So if you decrease to oppose, I need to increase. So I'm going to draw the graph. So now which side will be favored? The reverse reaction. So meaning the reverse reaction will be favored. H2 is going to increase, N2, it will be the increase. So once you see this shape, it's an increase. What about H2? H2 also is an increase. But now, what about the ammonia? Because I don't favor the ammonia, I'm favoring the reverse reaction. That will be the graph of concentration versus time. So this side, I'm going to draw a graph of what? I'm going to draw the graph of rate versus time graph. So I'll be drawing the graph of rate versus time. Rate versus time. So now the forward reaction, I'm having the forward reaction. I'm having this the reaction, the forward and the reverse. So the forward reaction is dotted lines. So this one is forward. The reverse reaction is a solid line. So now we draw the graph. This one is the forward reaction. This one is the reverse reaction, not reversible. Reversible is when the product can be converted back to the reactants. So now this is T1, this one it will be T2 there. So what I want to do, I want to decrease the pressure. I need to decrease in the pressure, decrease both. So decreasing both forward and the reverse. But which side will be favored? The reverse reaction will be favored. So the one that will be favored is going to decrease less. We don't favor this one will increase more until we do what? Now we need to work on the disturbance. By opposing the disturbance, we need to increase it. This is the Chatelain principle. So the one at the top, the one at the top must be the one which is favored. So now we favor the reverse, which is the solid line. So the solid line is on top of now the broken one. All right, so pressure and temperature, we look at this part here, more or less, if you look at the temperature and the pressure, more or less are similar. But the concentration, let us look at the concentration, which is the last one on these factors. The increase in concentration of a product. So they're having the concentration, one spike. Concentration, one spike. So an increase in concentration of a product. So product is ammonia. So I'm having one spike. So I'm happy. Now it's one spike there. You can use different colors. So one spike for nitrogen. If I'm adding actually here in the papers, the increase you'll see, you add more of this, adding more of what? Of the product, adding more of the product. So now which side will be favored? So we are adding more of the product, so I favor the reverse reaction. So now this one, the reverse reaction will be favored. So now reverse reaction, the reverse reaction, which is H2, the H2 will be favored. It will be the increase What about H2 will be favored? It will be the decrease. Because now, remember, this is the disturbance at equilibrium. By adding more of hydrogen, so according to the Chatelain principle, I need to do what? I need to oppose the disturbance. So to oppose the disturbance, meaning I'm going to decrease it. So meaning I'm going to do what? I'm going to decrease it. So I need to decrease it until such that the new equilibrium is going to be reinstated. All right. Then now I want to draw the graph. I can see more or less we are on the same page. More or less we are on the same page. I'm going to draw the graph. This will be the graph of what? This will be the rate. This will be the rate, and then versus time in seconds. So, okay, now this is the forward reaction. So this one will be the reverse reaction. So we have this graph there, okay? When I'm making this one to be, okay. Okay, what about this one? Can redraw it. All right, so somewhere there, this is T1. This will be somewhere there, and T2. T1 and T2, between T1 and T2, the system is at equilibrium. So the pressure, I know the pressure will be that in proportion to the volume. So now you decrease, not the pressure, I'm sorry. This is the concentration. One spike is a concentration. So now, which side is favored? The reverse reaction. So I'll be having the solid is the reverse. This one is forward. So this one is the concentration. So now I'm going to favor the reverse reaction. So I'm going to favor the reverse reaction. So now there's an increase. There's an increase in concentration. So I'm going to favor the reverse, which is the solid line. Then what about the forward reaction? So forward reaction will have the dotted lines. So the forward reaction will be this one. So the reverse reaction was favored. So reverse reaction, let me undo this one. It's favored. Let me draw this one is because it's a concentration. So then now according to the Chatelain principle, I need to work on the disturbance. So we need to be careful of what? Now, this is interesting part. This part here, we need to be careful with this part here. It's different to pressure and also the temperature. Remember, this is an increase also. This increases both forward and the reverse in terms of rate. But look at the corner there, compared to what? Compared to one of the temperature as well as the pressure. More or less, pressure and the temperature are the same. You look at the corner there, you look at this part here. So coming to concentration will be different. So this one, it will be the concentration. Okay, now, which side is favored? The reverse reaction is favored, yes, because I'm increasing this side, the product. If you're increasing, you are adding more of ammonia, the reverse reaction will be favored. So the reverse, which is the solid line, will be on top of the dotted line. So this is how we interpret the graph of rate versus time graph. Okay, so I'm having So that was the last one. Before we can just have a look at the questions, I'm having decrease in pressure, the concentration of the product. We can also now change it to saying, what about the reactants? We can draw the graph of that. But once we have this graph here, like look at the beginning there. So this is how we identify the concentration. Okay. So because today you are not going to spend more time on the graphs as you are going to prepare yourself for tomorrow, I'm having few, this is the application of the Chatelain principle, but let us look at few questions based on rate, especially the rate. I know the rate graph are more challenging compared to concentration versus time graph. Okay. Now, nitrogen and hydrogen are placed in an empty container, which is then sealed and now to react until equilibrium is reached, according to the following balanced chemical equation. So now this is a chemical equation. Which one of the following best describe the change made at T at 40 seconds? So we look at T at 40 seconds. 40 seconds. There was a disturbance. Is it increase in temperature? Now, increase in pressure, decrease in temperature, decrease in pressure. Okay. The first one, which is A, the increase in temperature. Okay, we look at our delta H is greater than 0. So the forward reaction there will be our endo. The reverse will be end exon. So now the spike, okay, let me explain something there. You look at the decrease and decrease, but according to the spike, it must be the increase. So C and D, they are out because the spike is facing up. So you are trying to eliminate the two questions that will be incorrect in your answer. So the C and D, there's a decrease and decrease, but the spike is facing up. It must be the increase and increase. So you want to see if there is an increase in temperature. If I'm going to increase the temperature, I'm going to favor. So now my dotted lines will be the forward, then the solid line will be the reverse. So I'm going to increase the temperature. The forward reaction is an endo. An increase in temperature, we favor endo. So the forward reaction, let us look at the forward reaction is on top of that one. Okay, might be correct one. We want to see good people. The forward reaction, so the reverse is a solid. Okay, the forward is that one. Let me check if pressure. I'm having 2 volume on the left-hand side. I'm having 4 volume on the right-hand side. I want to see if there's maybe the pressure. The pressure and the volume, I'm increasing the pressure. I'm going to favor the side where I'm going to have the fewer number of moles of the volume, meaning I'm going to favor the ammonia, which is what? The reverse reaction. Is it the reverse reaction favored there? So number 15, I see A there. I don't know whether you agree with me or what. I see A there. Because what I'm doing now, the spike is facing up. So now the forward direction is this one. The forward reaction is the broken line, which is this one. The reverse reaction is the solid line. So I'm increasing the temperature. I'm favoring the forward reaction. So forward reaction is favored, which is the dotted line. So 15, I go with A. Okay. If maybe you are disagree, you are agree, just raise up your hand if you have any query on that one. I'm taking my time also this side. This one, 20. Hypothetical chemical reaction in a closed container is represented by the following chemical equation. So our delta H is less than 0. The graph below represents the rate of the forward and the reverse reaction plotted against time. So now, which one of the following statements correctly describe the factors that could have caused the change in reaction rate? So if you look at this one, there's one of the catalyst, or I didn't mention the catalyst. The catalyst now favor both forward and the reverse reaction with the same rate. So if I can have a reaction like, I'm having this reaction, why now? I want the pen. I'm having H2 as a gas plus now maybe I2 as a gas, the forward, the reverse, 2HI as a gas. So if you look at this reaction, I'm having 2 volume of a gas, I'm having 2 volume of a gas. So the pressure will increase both forward and the reverse. Actually, between 30 to 50, there are 2 conditions. If I'm having this reaction, it might be the catalyst was added. Catalyst is the first one. The second one, it will be pressure increased. But if the reaction is similar to this one, 2 volume and 2 volume, so there are 2 conditions, is the catalyst being added and also the pressure was increased. So now let us look at this one. Now the disturbance at 30 seconds. So the disturbance at 30 seconds, is either talk about the catalyst was added, where's another catalyst? There's also the pressure there. Look at this one, the pressure. Then we go to our balancing equation. What we have on the left-hand side, the volume. I'm having this side, I'm having this a gas and gas, I'm having 3 volume. So what about this side? I'm having, is it 2 volume on this side? So it can be pressure being increased. So the temperature between which time? 30, it was a catalyst. 30, that was a catalyst. What about 50? The 50 seconds. There's a 30, and I'm not saying the answer is B. So catalyst was there. What about the temperature? The spike is facing down. So the temperature can be D. So I think, yeah, the temperature was decreased and the catalyst was added. So it will be B. B will be correct for this question there. Okay. Then the next one, I'm having the gas X2Y is introduced in the container, which is then sealed. The gas decomposes and reaction reaches equilibrium. The balanced chemical equation is shown below there. When a time is equal to 20 seconds, there was a change in the equilibrium. The graph below shows the changes in the rate of the forward and the reverse direction with time. Forward and the reverse. Okay. So at 20 there, which of the following could be the change made at time is equal to 20 seconds? So the spike is facing down. Is it catalyst? According to a catalyst, increases both forward and the reverse. So the catalyst will be out. Now, the concentration, the pressure was increased. If this is facing down, it must be the decrease. Now, the concentration of X2 was increased. It's facing down. It must be what? The temperature was decreased. So meaning the temperature was decreased. So the answer for that one will be C. Will be C. Okay. I think this one will be the last one on multiple choice questions. I have one question which is under rates of the reaction, or yeah, one question, the long question, yes. So for multiple choice, I'm having number 40 there. Consider the balanced chemical equation and the graph of amount versus time shown below. Amount of which is number of moles versus time. This one is the same as the concentration versus time graph. Okay. What change could have occurred at time T1? So the T1, this is the concentration, the delta H is greater than 0. If you have one spike, it must be a concentration. So meaning it can be the temperature, it can be the pressure. Pressure, I need to have how many spikes? 2 spikes for the reactants and also the product. So N2, if the spike is facing up, it can be added or the increase. If you talk about removed, it must be the decrease. So this one, it was removed. It's not the correct answer, but because, the spike is facing up. So this N2 was added on the reaction mixture. So the answer there will be A. Okay. Then now, long question, I'm having this question. Now we want to answer this question. Gabriel and Sarah repeat the experiment and make changes to the system. They use the result to plot the rate graph shown below. Okay, so this is the graph. All right, so we have T0 until we have T5 somewhere there. Okay, the T5 is somewhere there. So let me start with number 4 there. Okay, we'll answer 1, 2, 3 because it's an application of the Chatelain principle. At T5, NO2 is removed from the system. At T5, NO2 is removed from the system. Complete a sketch on the graph above for the change made if equilibrium is re-established at time T6. So now this is 3 marks. I want to complete the statement. So I'm not sure, is it N204? This one is a long question. I didn't write down. You see now. N204, 2NO2. Let's hope is the reaction. So now the forward is the solid line, the reverse. So this one is the forward. So then the reverse, it must be that one. So now what we do there, at T5, NO2 is removed. So then there's a decrease. We remove NO2. So the system want to do what? Want to replace NO2. By doing what? By favoring the forward reaction. So system want to replace NO2 because if we want to remove NO2, the system want to replace it. This one, remove. We are referring to what? Concentration. So we remove NO2. So once you remove, it must face down. The forward reaction, so the forward reaction we remove is going to face down. Okay, now which side we remove this one? The system want to replace it. Nah, okay. If we remove it, which side will be favored? Is it the forward or the reverse? So is it the forward direction will be favored or the reverse? We need to favor the forward reaction. So I want to check the graph again. I'm not sure whether I copied the correct one. So I want to remove NO2. So NO2, which is what? The forward reaction. So this one, the dotted line is the reverse, okay? The forward direction is the solid line. The forward direction is the solid line. So I remove NO2. We want to replace it. I'm going to favor the forward direction. The one that is favored will decrease less. So the one that is favored will decrease less, which is the forward will decrease less. Or it's a solid line. So this one is a dotted line. The one that is favored will decrease less. So then once you remove, remember this part there, I'm sorry about the part, that edge, the part there, it must be the forward. This is how you're going to draw it. The forward reaction will be favored. Then now the reverse reaction, because we don't favor the reverse, will decrease more. But now if the reaction was NO2 like this way, the forward, the reverse, actually it's supposed to be this way, N2O4. So now the graph will be, remember, at T4. So at T4, then at T5. So what about if the reaction was this way, 2NO2, the forward and the reverse, and 2O4. So what we need to do is to decrease the what? We remove NO2. So this one, we remove. So the system, we want to do what? We want to replace NO2 by favoring the reverse reaction. So the graph, this is how we're going to do the graph. We remove NO2. The system want to replace NO2. So we are going to favor the reverse reaction. The one which is favored is going to decrease less. So now the one that will be favored will decrease less. Then this one will be the solid line. Then until a new equilibrium will be established. So because this is a concentration, we look at this part here. All right, this is how the graph will look like. So how many marks? So between the new equilibrium at T6, the new equilibrium at T6, the new equilibrium will be established at T6 there. So that will be a new equilibrium. Okay, so that will be, this one is decreasing more, but at the end, oh, I'm sorry, this one must be solid. This one must be solid. So this one, the one that will be favored, it will be on top of the one which is not favored. We favor the reverse reaction. So the reverse reaction there, the reverse reaction will be this one, which is the broken line. Okay, so the other questions that are based on the Chatelain principle. So I'm going to share my notes. There will be the Chatelain principle somewhere there. The concentration versus time, an example, the rate, if we talk about the rate, increase in concentration of the product, this is how you're going to answer the question. For the rate graph, look at the bullet tree, and increasing concentration will increase the rate of both forward and the reverse reaction. The reverse reaction is favored and it will be greater increase in rate. It's increasing more than. So this is how you're going to answer the Chatelain principle there. So I'm going to share the notes. I'll share in the notes to educators. Now this reaction, just write it down. Educators, please note this reaction. We're going to use this one. We are going to use this reaction there. Okay. Now, how do the forward and the reverse reaction compare at T3? At T3, the forward and the reverse, if you compare the two, they are equal. It must be they are equal. Even between T3 and the T4, the system is at equilibrium. Both the rate of the forward and the reaction is equal. Okay. What change could have been made to the system at T2 if the equilibrium constant does not change? Now they're referring to the Kc value there. So at T2, at T2, you know, now I'm having a problem. I don't know whether the delta H is greater than 0 or is less than 0. But now we can figure it out. We can figure it out if the delta H is greater than 0. So let us look at now, if there is a pressure at T2, if delta, you know, now the delta H is a problem. Let me check pressure, if there's a pressure there. The pressure is in proportion to the volume. So now there's an increase. Once you see the sharp graph, so this is an increase in pressure. So now the increase in pressure, I'm going to favor the side where I'm having fewer number of moles. So I'll be having 2 volume this side, I'll be having 1 volume that side. So the pressure, if I'm increasing the pressure, which side that will be favored? I'm going to favor the forward reaction, which is N2O4. So now the solid line, it represents the forward. So the dotted line will represent the reverse. So if I'm increasing pressure, if I'm increasing pressure, I'm going to favor the forward reaction. So the forward reaction, according to that graph, is a solid line. The reverse is a dotted line. So the pressure, I'm favoring the forward. The forward direction is favored? No. So look at the pressure. Increase in pressure. Increase in pressure, I'm favoring the forward direction, which is the solid line. But look at that part there. So it can be pressure. What about the temperature? Now, I'm worried here, delta H. Let me see if delta H is greater than 0. If delta H is greater than 0, I'm increasing the temperature. I'm going to favor the forward reaction. The forward reaction is N2O4. The forward direction is N2O4, meaning it will be incorrect. So now the delta H was less than 0. The delta H was less than 0. I'm increasing temperature. This is the increase. Once it's facing up, is the increase. So I'm increasing the temperature. I'm increasing the temperature. The temperature was increased. The temperature was increased. If I'm increasing the temperature, the forward is an exo, I'm going to favor the reverse reaction. Reverse reaction will be favored. The reverse reaction will be favored. The reverse, the dotted line will be favored. So meaning now here, the temperature was increased. It must be, there's an increase in temperature. So, but now the question is, I think I did copy the wrong, the equation there. Remember, the Kc, if you talk about the temperature, the Kc does not change. It must be pressure, guys. Because once you, the temperature, the Kc to remain constant, it can be pressure. I mean, it can be the temperature. It can be the temperature because equilibrium constant does not change. It must be pressure. So, I'm struggling because I didn't copy the original equation. So I hope you are with me that side. Guys or colleagues, what change could have been made to the system at T2 if equilibrium constant does not change? So it can be the temperature. So it must be what? The pressure was increased. I hope it makes sense now, because once we say temperature, the temperature is going to affect the Kc value. Although I'm trying to see if my equation is correct or what. But once you talk about the temperature, the Kc is going to change. But according to that statement, equilibrium constant does not change. So it can't be the temperature. Oh, okay. At time T4, the temperature is increased. Now they talk about the temperature now. Now they talk about the temperature, meaning here it must be pressure. So at T4, the temperature is increased. Is the forward reaction exothermic or endothermic? Oh, now the delta H was not given, because now they are asking delta H, is it forward or the reverse? I mean, is it the endo or the exo? So at T4, there's an increase in temperature. Is it the forward reaction, exo or endo? So is it exo or endo? At T4, the delta H there, the delta H. So is it delta H? So the delta H, so is it, I'm not sure if this the reaction now, which one is which. Let me try to see if I'm using this one. Increasing temperature, which side is favored? The reverse reaction is favored. So the reverse reaction is favored. I want to see if I can do this. The reverse reaction is favored if I'm using this reaction. So now the forward reaction is an exo. I'm increasing the temperature. I'm going to favor the reverse reaction. So the reverse reaction is favored. So the delta H, according to my equation, this one, the delta H will be less than 0. But if you're using that one, let's check. If I'm using this one, if I'm saying delta H is less than 0, I'm increasing temperature. Increasing the temperature, I'm going to favor the reverse reaction. The reverse reaction, which is N2O4. I'm increasing temperature, I'm going to favor N2O4. So now, once we start there at the beginning, this will be, I'm almost finished, this will be N2O4. This will be the reversible, I'm sorry, the reversible, the forward, the reverse will be N2O4, N2O4. So the forward direction, it will be NO2. So now what we want to do here, I want to increase the temperature. Is it N2O4 favored, which is the reverse reaction? N2O4, N2O4, then okay, according to this, yes, is favored. What about on that reaction, on this reaction? So I'm increasing temperature. Is it NO2 favored? Is it NO2 favored? NO2, which is the solid one, no, it's not favored because it's at the bottom. I hope it makes sense on that side. So I want to apologize by not copying the correct equation, but look into our argument. If I'm using this one, so I'm increasing the temperature, I'm favoring the reverse reaction. I'm favoring the reverse reaction. So which is NO2 there. Is it NO2 favored, this one? Is it solid line on top of the broken line? No, it can't be that one. So it can't be this one. So now it's going to be that one. I'm sorry about the confusion that I've caused because I didn't copy the original equation. I forgot to copy the original equation. Okay. So then now you need to say the delta H, is it the delta H? Let's check the delta H. So I'm increasing the temperature. I'm going to favor. So the solid line will be the forward, the reverse one will be dotted line. Increasing temperature, I'm going to favor the reverse. I'm going to favor the reverse. Of course, it will be favored. So the delta H, according to this, the delta H will be the delta H will be less than 0, according to the question. Is it the forward direction, X or endo? The forward direction will be now exothermic reaction. So will be an exothermic reaction. So why you say it's an exo? So let us have the points. According to the Chatelain principle, the disturbance, we need to identify the disturbance. So now the increase in temperature, it is the disturbance on the system. The decrease in temperature, you're going to say increase in temperature, now favor. You'll write in full, ne? Favor end, which is endothermic reaction. So then now, which endo is it, forward or the reverse? Is the reverse. So you're going to say now reverse reaction is endo. So now, which side will be favored? Are you going to favor the forward or the reverse? Now, reverse reaction will be favored. So the reverse reaction will be favored. So that will be the answer for that one. The first mark, you identify, is it exo or endo? Let me use the different color there. So it will be 1 mark for this. Then now it will be 1, 2, 3. So this is going to count 4 marks for that. Thank you very much, guys, for being patient with me. The presentation, I'm going to share it with colleagues. Then I'm going to include the equation there at the top, because this one of N2, NO2 to N2O4, it was confusing me because I didn't copy the equation, okay? Thank you very much for your patience. If you have any question, you can just raise up your hand, or if no questions, I'm happy with this presentation. Thank you very much. Until we meet again, remember, every Thursday we are going to have these sessions. So I hope next time I'm going to rectify this mistake by not copying the equation at the top there. Thank you very much. Bye-bye.